Okay, hello everyone. So we are very welcome Xinlu from Eastern China Normal University, who will give us a talk on the Coleman conjecture on the finiteness of CM curves. Okay, Xinlu, it's your turn.
Okay, thanks very much for the introduction and the invitation. In this talk, I will give a brief introduction to this conjecture and some of its recent progress. So first, let's start with the content of this conjecture. So first, we need two definitions. The first is the CM abelian varieties. We will always consider over the complex number. So an abelian variety is just a CG model sum lattice. So an abelian variety of dimension G is called CM. If its endomorphic ring contains a commutative algebra of very large rank, that is, its rank is equal to 2G. If we use the Poincare theorem on abelian variety, we know that an abelian variety is isogenious to a product of irreducible abelian variety. Then if we use this theorem, an abelian variety is CM, it just says that every irreducible sub abelian variety is CM, and for an irreducible abelian variety, it is CM just means its endomorphic ring is a CM field. So another notion is about CM curve. And curve is called CM just means its Jacobi is the same abelian variety. So for Q, we can consider its Jacobi. So this is just from this same abelian variety. Okay, it is known that there are many same abelian varieties. For example, if you because you give if you give a same field, you can construct as an abelian variety whose endomorphic ring is just this same field. We know that there are many same fields, so there are many same abelian varieties. But for the Qs, it is not so good. I mean, very late curves are known to be CM. The typical examples are given by the Qs with sufficient many automorphisms. Yeah, for abelian variety, an abelian variety is CM just means that its endomorphic ring contains a sufficient large commutative algebra. Or you can think that this abelian variety should have some symmetry. So for a Q, it also means that this Q should have some symmetry and many symmetry. So the up to now the same Qs are only limited to these Qs with sufficient many automorphisms. For example, the Fermat Qs and also the cyclic cover of P1 nullified over 3 points. But all this kind of construction can only you can only get finite many CM Qs for a fixed genus G. So this because of this we have the following conjecture of Coleman. So the Coleman conjecture just says that for a given genus G at least 4, there exists up to isomorphism at most finite many CM algebraic curves of genus G. So the statement of the Coleman conjecture is very simple. But if you value this this version of this conjecture, it is not easy to solve this conjecture because on the one hand, if you start with same abelian variety, it is not easy to know whether it is an Jacobian or not. Or if you, or on the other hand, you do in another direction, you start with an algebraic curve. Of course, you can compute its Jacobi, but it is very difficult to compute its endomorphism ring. So it is not easy to decide whether it is same or not. So we may need to restate this conjecture, use restate this conjecture in another language. So first we use the language of modular space. So let MG be the modular space of algebraic curves, and AG is just the modular space of principal polarized abelian variety. And we have a lateral map from MG to AG, just the Taylor map. It maps this C to its Jacobi. And we denote by this AGCM is the same, the subset correspond to same abelian variety. So if we use this language, the Coleman conjecture can be stated as follows. So it just means that this J is just a Taylor map. So this Coleman conjecture says that the inverse image of this CM subset is finite many. So, or equivalent if we just vary this MG as a subset of AG, then this just means that the intersection of MG with the same points is finite many. Yeah, here we can first we can see that why this Coleman conjecture requires this genus G is at least 4, because for G is equal to 2 or 3, this MG is just equal to AG. So we know that there are this same point in AG is dense. So there are also many same algebraic curves when G is equal to 2 or 3. So, but for when G is at least 4, we know that this MG is a strict subset or strict subvert of AG. So it is not easy to see whether the same point lies in MG or not. Here we can see that the challenge part of this problem. We know that this same subset is characteristic dense in AG, and now MG is a subvert in AG. So this conjecture says roughly that a subvariety intersect a subset which is characteristic dense in AG. But this intersection, conjecture says that this intersection should be finite many. Just like that, this subvariety lies in the interspace of this same point. So such kind of problem, there are many such kind of problems in mathematical problem. For example, in the number theory, the famous conjecture of Coleman is famous conjecture of Mordell is such a problem. In fact, this Coleman conjecture is an analogous to Mordell's conjecture and Manin-Mumford's conjecture. So the classical, here we recall the classical conjecture of Mordell, the Mordell conjecture. So the Mordell conjecture says that for an algebraic curve of genus at least 2, the natural point on this algebraic curve should be finite many. Yeah, we know that if you if you write this algebraic curve in project space, we know that the natural point in the project space is the direct dense, and this just says that this this QC should intersect this natural point in that project space is finite many. So it is in this way we can see that we may value this Coleman's conjecture and the Mordell conjecture. There are some analogy here, and there are another conjecture is the Manin-Mumford conjecture. And this Manin-Mumford conjecture is in fact also an analogy to Mordell's conjecture. This conjecture says that for an algebraic curve of genus G at least 2, and we put this Q into its Jacobi, and this on this Jacobi, its Jacobi is an abelian variety, so we can talk about the torsion point on that abelian variety. It's just the points that upon P is the torsion just means that the P plus P plus P plus n times it is equal to the origin of this abelian variety. So this the conjecture of Manin-Mumford says that this QC intersect with the Jacob intersect this torsion point is finite many. This is if you consider it as an analog of this Mordell conjecture, just replace this natural point by the torsion point. Okay, these two conjectures have a high dimension knowledge. Here is the Manin-Mumford conjecture, the high dimensional version. So let X just say a subvariety in an abelian variety A. Then if X is not a translate of abelian subvariety, then this X intersect with the torsion point is not the distance in X. Okay, the Mordell conjecture and the Manin-Mumford conjecture are both proved now. So there are theorems now. Okay. Actually, before these two conjectures are proved, now have already realized that these two conjectures can be unified in one conjecture. Now, as the Mordell-Nance conjecture, this conjecture is also proved now. This conjecture says that when for a subvariety and abelian variety A, and we consider a finite generate subgroup and its divisible whole, just means that n times this x plus s plus n times belongs to this finite generate subgroup. So if X is not a translate of an abelian subvariety, then X intersect with this gamma is not the distance in X. Okay, we can see we can give a proof implication of this Mordell-Nance conjecture to Mordell conjecture and the Manin-Mumford conjecture. So for the Mordell conjecture, we can just take X equal to C and A just is Jacobi, and the gamma equal to lambda equal to the natural point of A here. X is equal to C and A is Jacobi of C. Then it just means that this C lies in its Jacobi, and this the intersection of C with the natural point of this Jacobi. So just means that the natural point on C is finite many. Here, I think it's due to V that the natural point of A is finite generated. And for the Manin-Mumford conjecture, we can just take also X equal to this QC, and A is this Jacobi, and the gamma is just the original point of this Jacobi. So this just a point, so it is must be finite generated. And gamma is its torsion point. The torsion point is the divisible whole of this this original point. Okay. Then this Mordell nonce conjecture is just the Manin-Mumford conjecture. And of course, for the high dimensional Manin-Mumford conjecture, we can just take this gamma equal to the origin, and lambda is the torsion point on this abelian variety. So this is the classical conjecture of Mordell and Manin-Mumford. How the conjecture of Coleman, I mean the Coleman conjecture is an analogy of Mordell's conjecture, but how this comes? For this, we need to consider another notion in number theorem. It is the Shimura variety. Okay, here I'm not going to the exact definition of Shimura variety. Roughly speaking, and Shimura variety is a causal space related to some algebraic group G, and there are also here special subvariety in special subvariety, which is analogous to the transnet of transnet of abelian subvariety in an abelian variety. So for us, it is enough to keep in mind that AG is a Shimura variety. Okay, so here, when this Shimura variety AG is an analogy of abelian variety, so AG, the same point and AG is analogy to the torsion points, and the transnet of abelian variety is correspond to the special subvariety. So now we recall that the Coleman conjecture just says that MG intersect with the same point of AG is finite many. So this is very similar to the statement of Manin-Mumford conjecture. Yeah, Manin-Mumford conjecture just says that, okay, we come here. Okay, Manin-Mumford conjecture just says that for an algebraic cube C and consider the torsion point, then this C intersect with the torsion point is finite many. And now the conjecture of Coleman just replace this QC by the module space of Qs. And by its an abelian variety is the Jacobian of C, replace this Jacobi by the module space of abelian variety. So just means that the Manin-Mumford conjecture says that C intersects with the torsion point in its Jacobi is finite many. This conjecture says that the model space of MG, the model space of Qs intersect with the same point in AG is finite many. Okay, this is the Coleman conjecture. It is analogous to the Manin-Mumford conjecture, the one-dimensional case of Manin-Mumford conjecture. And we have already said the Manin-Mumford conjecture also has a high-dimensional analogies. So for the high-dimensional, if we state it in the language of this AG, then it is another conjecture, not the Coleman conjecture. It is a conjecture of André-Oort. So, okay, first we record the Manin-Mumford conjecture here. High-dimensional case just means a subvariety in an abelian variety A, and A torsion is its torsion point. So if X is not a transnet of abelian subvariety, then this X intersect with the torsion point is not direct extents in X. So if we replace this X, replace this A by AG, so it is replace the abelian variety by the Shimura variety AG, and the torsion point is replaced by the same point, and the transnet of abelian subvariety is replaced by special subvariety, then we get the André-Oort conjecture. So that X is the subvariety in AG, and if X is not a transnet of abelian subvariety, so here is if X is not a special subvariety, then X intersect with the same point is not the reference in X. So this is is an analogous of Manin-Mumford, the high-dimensional Manin-Mumford conjecture. And the Coleman conjecture is just the one-dimensional case. For the Manin-Mumford conjecture, we know that the high-dimensional, the one-dimensional case is just a special case of the general case, the high-dimensional case. But for here, this Coleman conjecture is independent from the André-Oort conjecture. I mean, the André-Oort conjecture cannot imply the Coleman conjecture. Okay, this is the another conjecture. It is also an analogy to the Manin-Mumford conjecture. Here, you can also state this statement has another version. So just means that if you take a subset in the same point, you take its size closure, it is a finite union of special subvariety. Okay, so based on this conjecture, Oort made another conjecture, which we will see that which we will see is equivalent to Coleman's conjecture. So let's first state the conjecture. This conjecture, it says that for a special subvariety of AG, Oort conjecture says that this X intersect with MG is not the extents in X. So this conjecture means that if you are given any special subvariety in AG, then this special subvariety should not generally in MG. Here we say subvariety is generally in MG just means X intersect with MG is the extents in X. So Oort conjecture just says that there does not exist any special subvariety of positive dimension generically in MG. Just means that if a special subvariety generically in MG, then it must be zero-dimensional. Just the zero-dimensional space subvariety that is the same point. So based on this André-Oort conjecture, we know that the Oort's conjecture, the Oort conjecture is equivalent to Coleman's conjecture. So here we just give an implication of both sides. So from Oort conjecture to Coleman conjecture. So Coleman conjecture says that this subset should be finite many. So MG intersect with AGCM is finite many. So we prove this by conjecture if this subset is not finite many. So if this is a subset consists of infinite many points, then you can take its Zari's closure. Then by the André-Oort conjecture, you take the Zari's closure of some same points, then you will get this Zari's closure should be a finite many of special subvariety. So because this subset is infinite many, so its Zari's closure, if you write it as a finite many special subvariety, then at least one of them is of positive dimension. So we will assume that their xi is of positive dimension, and by constructor we say that xi in this MG, the xi intersect with MG is the residence in xi. This will contradict the Coleman conjecture, the Oort conjecture. So from Oort to Coleman, from this Oort conjecture to Coleman conjecture. And for the another direction, from the Coleman conjecture to Oort conjecture, the Oort conjecture just says that if you are giving special subword X in AG, then X intersect with MG is not direct space in X. Okay, here we still prove it by contradiction. So we assume here X intersect with MG is direct space in X. Then we know that because MG is locally closed in AG, so X intersect with MG is open in X. If X intersect with MG is direct space in X. So here we get an open subset in X. But on the other hand, because X is special, so for a special subword, its same point is direct space in X. So we get that the MG intersect with AG should contain this subset, but this subset is infinite. This contradicts the Coleman conjecture. So, so now we see that these two the conjecture of Coleman and the conjecture of Oort is equivalent, and we will call these two conjectures together as Coleman-Oort conjecture. Yeah, it just has two different explanation forms. One is given by Coleman and another is given by Oort. Okay, this is the statement of the Coleman-Oort conjecture. Okay, next we will record some of the progress toward this conjecture. Okay. First, it is not a good news. It is a bad news that for low general, there are counterexamples to this conjecture. Namely, for G from 4 to 7, there exists a special subword of positive dimension generically in MG. This example can be constructed very explicitly. Here, for example, here and for each G, and one example here. And then we see this when G is equal to 7, this is given by a cyclic cover of degree 9 of P1, non-further over 0, 1, and infinity, and the point T. When this T moves in P1, you get a one-dimensional subword in MG, and it is shown that this one-dimensional subword is special. So for the low general, this conjecture is the Coleman-Oort conjecture is not true. So if we want to write this still as a conjecture, we still we have to give some restriction on the genus. So up to now, the correct statement of this conjecture should be the following. So for sufficient larger genus G, or at least you should larger or equal to 8, because for G from 4 to 7, there are counterexamples. So for sufficient larger genus G, it holds this intersection the same cubes is finite many. Yeah, this is just the same cubes. So while equivalent, if you use the language of Oort, just says that there does not exist any special subword of positive dimension generically in MG. Okay, why this is still a conjecture, whether there exist counterexamples? Okay, perhaps because as we said before, that this conjecture is an analogy of the famous Mordell conjecture and the Manin-Mumford conjecture. And these two conjecture, I mean the Mordell conjecture and the Manin-Mumford conjecture, are proved to be true. So people are most likely to believe this Coleman-Oort conjecture should be also true. Just like the Mordell conjecture, the Mordell conjecture requires the genus G is at least 2. Yeah, for G is equal to 1, as there is elliptic curves. I mean, and elliptic curves can have infinite many national points. The Mordell conjecture requires the genus G is at least 2. So here we just put some restriction on the genus G. So most people believe this conjecture should be true. Okay, so next I will go to the progress of this conjecture. So because this conjecture, okay, up to now it is still open. So there the following is just some progress to this conjecture. So this conjecture, as we say, that it has two different versions. First is given by Coleman, and the second is given by Oort. So Oort's statement just says that there does not exist special subvert of third dimension generally in MG. So so the authors along the author's statement, we can do this conjecture in two different ways. So first, people prove that some natural subvert of MG is not special, or you give some special subvert in AG and then prove it is not generally in MG. This is the along the statement of author, and another is along the statement of column just prove some finiteness of CM curves of some special type. If you prove all, then it is the conjecture. Okay, so first it is a progress due to Dvorak and August. They prove that the MG is itself not special. Okay, if MG is special, then nothing need to do. Another progress is due to Manin. He proved that the following subvert is not special. This CMN, give a trip here. M is a natural number, and N is a natural number, and A is A1 to AN. This CMNA is a subvert of MG consists of curves of the following forms. It is a cyclic cover of degree M, cyclic cover of P1 of degree M, normified over N point, and the normification index is this normification data is A1 to AN. It just means that a cube in this space has an affine equation of this form. Okay, why Manin consider this subvert? Because for G from 4 to 7 here, the contact example are constructed in this way. For G equal to 4 to 7, this contact example are all constructed in this way. You do a cyclic cover of P1 normified over some points, and you fix the three of them as 0, 1, infinity, and move the other. You get subvert in MG, and some of this variety in MG is special. Find them here, and here Manin proves that if you do this construction, when this genus G is large, when genus G is at least 8, then you cannot get more contact example. In this way, you cannot get contact example to the Coleman-Oort conjecture. He proved that for such kind of subvert of MG, it is not special. In fact, he proved that such subvert is special if and only if it is isomorphic to the following 20 families. Yeah, here 20 families. The largest genus is 7. You cannot get more. Okay. And Monocelum was generalized to abelian cover or also Galois covers. This includes the works of Fredenia Jage and Penigani and Mohaya Zhou. Another lateral subvariety is the subspace consists of Kegler curves. Here, Kegler just means that such a Q admits a degree K cover of P1, and this K is the minimal possible possibility. So here they prove that this decay is not spatial. Yeah. In fact, they prove that they give an upper bound of the possible spatial subvariety in decay. In particular, we know that an algebraic curve of genus G, its colarity is at most G over 2, something like that. So then you can get that any possible spatial subvariety generated in MG, its dimension is at most 502 times G minus 1. So, well, in particular, you know that MG is not spatial. This is the work of Dweck and Vogels. Yeah. Another subvariety of MG is the minimum dimensional case. I mean, we consider the positive dimension. So the minimum dimension is 1 dimension, just the Shimura curves. So here are also some results here. So in the work of Frederick Zhou, they prove that a natural curve in MG with n Caspers, then we know that the Casper is at least 4. And if the Casper is exactly 4, then we know that the C is spatial. And a result of calculus says that for a natural curve, there are functional here. There are functional depend on the number of Caspers, such that if G is sufficiently large with this number, then C is not spatial. And with Tang, Xu, and Zhou, we prove that for G is at least 4, there does not exist any rational curve in MG with 4 Caspers. Here,
so what is a C? C just any rational curve, or is there some restriction?
C is a rational curve.
Just a rational curve with n Caspers.
Yes.
Okay. So then
it can lies in MG, then n is at least 4.
But what do you mean by Shimura curve here? So I
mean, here we do not require this is Shimura for any Q. This Caspers is at least 4, and when it is equal to 4, then this C must be Shimura.
Oh, I see.
Yeah.
Could it be totally geodesic in AG rather than spatial?
Pardon?
Could it be of weakly spatial in AG rather than spatial? How do you distinguish between spatial and weakly spatial subvarieties here?
There in the work of Frederick Zhou, they give a calculated ratio of this spatial subvariety. They use this Alkerf inequality. When that inequality is an equality, then that Q is weakly spatial. Yeah.
Okay.
And when a weakly spatial Q's contains a same point, it is spatial.
Mm-hmm.
Okay. Another progress is to show you pick some special subwords in AG and prove they are not generic in MG. So first, André-Oort says that if you give a special subword in generic in MG, and if you here he requires some technical restriction here. He can prove that this X is bulk causal, or it has some strong geometric restriction. I mean, X intersected with this hyperadditive locus is a divisor. And a theorem of Jota proved that for any possible spatial subword in MG, he gave a restriction on this boundary of this spatial subword. I mean, if you consider the boundary of X, here we consider this this MERR is the boundary of MG correspond to this irreducible curves. Then he proved that the boundary of X does not intersect with this MERR. Just means that the boundary of X cannot correspond to an irreducible curve. Yeah. Here is a result of De Jong and Shou Zhang, and also here De Jong and Zhang prove this result for genus G at least 5, and Bainbridge and Muller prove this result for G is equal to 4. So together they prove that when G is at least 4, the MG does not contain any Hebel module subword. And together with Chen and Zhou, we prove there are some results about the space subword of SUN type and the orthogonal type. So here, our result is proof that if X is a space subword of SUN1 type, then X is not generic in MG if some numerical inequality hold. Here, our condition involves not only G but also N and D. So it is not complete toward this Coleman-Oort conjecture. Yeah. Another result is also reduced to the Q case. First, the Muller proved that in MG, very special Shimura curve is not in MG. They proved that he proved that when G is at least 6, MG does not contain any Shimura curve. Here is very special Shimura curves. Means that this curve is not only Shimura but also Teichmüller. We proved that we excluded some Shimura curve of Mumford type. Here a Q is called Mumford type. Okay. Mumford used the Color structure of continuous algebra of a total real cubic field to construct an example of Shimura word, which is lot PL type, and we can generalize this construction to construct Shimura curves in high genus. Just use the replace this cubic field by some total real field of degree D. Okay, and also we prove that this hyperelliptic locus does not contain any special curve when this G is at least 8. This is some progress to this conjecture. Use the language of use the author's statement. Finally, we state two progress to this conjecture. Use the statement of Coleman. First is due to Dye and Oort. They prove that the YSM, they prove that there are at most finite many YSM cubes. That is, MG intersect with the YSM point is finite many for fixed genus G at least 4. Here, the YSM same cubes is the definition is following. First, we consider the CM field L. So, a CM field is called well if the normal closure of L is the Galois group is the largest possible. The Galois group is equal to this one. So this just a very special CM field. So an abelian word A is called YCM if its endomorphism ring contains a YCM field. Just its endomorphism is equal to this YCM field. So if its endomorphism ring is a field, it just means it implies that this abelian word is simple, is irreducible. So an abelian cube is called CM if its Jacobian is YCM abelian word. So Dye and Oort's result is about the YCM point, YCM cubes. So here YCM abelian word is a very special case of CM abelian word. But they prove in their paper they prove that the YCM point is also directly dense in AG. This is in fact you just need to prove that there exists one such CM abelian word. If you have one such CM abelian word, you take the Hecke translation, then you will get a direct dense subset. But in their paper, they also ask a question to find an example. I mean, they prove that this intersection is finite many, but they do not know any example. Okay. Here, together with Chen and Zhou, we prove the following finiteness result. So for any genus G is at least 8, then there exists at most finite many CM subelliptic curves. Here, subelliptic curve, the definition is the following. An algebraic curve is called subelliptic if it has a equation of the form y of n is equal to fx. Here, fx is a separable polynomial. This is just generalization of hyperelliptic curves. Yeah, hyperelliptic curves means here is y squared equal to fx. So SG is the subelliptic curves. So we prove that there are at most finite many CM subelliptic curves. So in particular, we know that for any genus G for any genus G at least 8, there are at most finite many CM hyperelliptic curves. Yeah, because here hyperelliptic is just a special case of superelliptic curves. Okay. Okay, we still have 10 minutes, so I will in the next part I'll give a sketch proof of the last CM. So here is this statement says that there are at most finite many CM superelliptic curves. So if you use the language of Oort, it just says that there does not exist any special subword of positive dimension generated in this SG shop-edible locus. So our proof is to use the statement of author. So we will prove by contradiction. So we assume there exists a special subvariety of positive dimension in SG, and then to derive a contradiction. So the proof is divided to 2 steps. The first step is reduction to the Q case. So we prove the following theorem. So if the shop-elliptic locus SG contains generic and special subvariety of positive dimension, if and only if it contains generic and Shimura curves. So use this theorem, we can reduce this on theorem to the Q case to exclude Shimura curve in SG. So the proof of this the reduction theorem consists of 3 points. So first is that for any special subvariety in AG, if you use this parabolic compactification of X, you can prove that either this X contains a Shimura curve or its boundary is of count dimension at least 2. Another point is that the edge decomposable, I mean, the abelian variety of decomposable type, that is an abelian variety isomorphic to the product of two abelian subvariety of low dimension. This locus is a union of special subvariety. And last point is that the affineness of SG, I mean, the shop-elliptic locus contains no projective curve. So if we sketch the proof, there is the following. So if you assume that SG contains generic and special subvariety of positive dimension, so we pick X as such a special subvariety of minimum dimension. So we we are going to prove that if SG contains a special subvariety of positive dimension, then it must contain a Shimura curve. So if we pick such X of minimum dimension, we can assume this X is of dimension at least 2. If it is 1, it is a Shimura curve, so we are done. So if X is dimension of at least 2, so first we know that the boundary is co-dimension at least 2. So if we can choose a projective curve C in X, because the boundary is at least 2. So a generic curve will not pass through the boundary. So you will get a projective curve in X. And another point is that this AG decomposable abelian variety is a union of special subvariety. So you intersect with X, you will get a special subvariety of X, but X is of minimum dimensional. Okay, then so you will get that the intersection of X with this AG decomposable is 0 dimensional. Because it is a special subvariety of X, so it must be 0 dimensional. So we can even assure that the projective curve in the first step is satisfied that C intersect with the decomposable locus is empty. But so now this X, okay, this subset is nothing but this X intersect with this decomposable locus. So in the by the above process, we get a projective curve C in this SG. But now we get a contradiction because we know that SG cannot contain a projective curve because SG is affine. So we get a contradiction. Okay. So this is the first step. We reduce the cell to the Shimura curve case. So step 2 is to exclude the Shimura Qs. So for the step 2 is much more technical. So the main idea is to study the Higgs bundle for the family of same step Schopenhauer cubes associated to such a Shimura cube. So here, here C lies in. We assume that C is a Shimura cube in the superadditive locus. So we can consider the family of cubes over this C. Of course, here there are some technical point here. You need to because MG is not a fine model space. You need to take some naive structure. Anyway, you can get a family of cube over C, and you do the compactification, and you can consider this the VHS on this base QC. And the linear extension and take the gradient, you will get a Higgs bundle. Yeah. For the Higgs bundle, we have the Fourier decomposition. I mean, a Higgs bundle can be decomposed into two parts. One part is with ample one zero part, and the other is with zero Higgs field. And use Higgs correspondence. This is just this corresponds to a decomposition on the local system. So for the local system, we have a decomposition into two parts. Okay, so to simplify the situation, we just consider the most simple case. That is when the Shimura cube C lies in SP, and we consider the when n is when n is equal to p is a prime number, and C is non-compact. So there are the proof we are divided into several steps. So first first step is to show that this unitary subsystem is non-trivial. I mean, here the decomposition here, the Fourier decomposition decomposes this Higgs bundle into two parts. This net part is the unitary part, and this corresponds to decomposition on this local system. So the first step is to prove this unitary sublocal system is non-zero, and then prove this this non-zero unitary sublocal system is in fact trivial. I mean, it is a trivial. It is a direct sum of trivial local system, and by samples correspondence, this just means that the family is irregular, which means that this relative irregularity is positive. This is the one form on this the total space S, and this is the one form on C. So this just means that S admits more one form than the base cube C. And the second step is to prove this this irregular family F is horizontal. Just means that we can we can construct a ladder fabulation such that all this one form here, all this one form in the first step comes from this fabulation. I mean, we can construct a ladder fabulation such that the base of the ladder fabulation, the genus of the base is just equal to this relative irregularity. So, so up to now, we see that on this family of cube S, on this total space S, this is a two-dimensional variety. So it admits two fabulation. The first is the original fabulation over the C, and we can get this. There is another fabulation. So on this S, we have two fabulations. So this S should have some strong geometry property. And
what is this F bar prime? So is this relative algorithm F or some other things?
This is we can construct. I mean, from the first step, we need to prove. I mean, for in n equal to p case, we can prove that on S bar there must exist a larger fabulation. In general, for fabulation, we cannot assume there are a larger fabulation. Here the base of this larger fabulation is positive. I mean, it is not a rational code.
Okay.
And then the third step is to use this geometry of this horizontal family of cubes to establish a slope inequality. I mean, to prove a slope inequality of the form, that is the intersection of this relative caloric bundle is at least of this number. This is some terms comes from the singular locus. And the fourth step is to prove use the logarithmic McDowell inequality to prove an inequality of this form. This is called a caloric inequality. So this gives an up bundle on this the self intersection of this relative caloric bundle. But this term and this term are not the same. Just some terms comes from the singular locus. And finally, we will use the Favre-George characterization on these Shimura curves. And their characterization gives a connection between this number and this number. So finally we will put this together. You will get a contradiction. Okay. Thank you. I'm sorry. Okay.
Okay. So thank you very much. Thank you. So, are there any questions? Maybe some questions.
So, but what do you use from CM theory? Somehow, I mean, all these arguments are kind of geometrical, right? I'm a bit confused by what all the arguments. All the arguments you presented are of geometric flavor, right?
Yeah.
But then you have to use this information about CM points and some maybe CM theory or things like that. But what do you use from CM theory?
In our proof here for the Q case, we do not use the CM field. We mainly use the Favre-George characterization for Shimura curves.
Okay.
Yeah, this is the last one.
Okay, are there other questions? Okay, if there's no questions, so let's thank the speaker again. Okay, thank you, Xinli.